Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 1, Lesson 11 on geometry in the coordinate plane. So you've worked before in the coordinate plane. In fact, you started working in the coordinate plane in 6th grade math. That's a while ago, right? And you may have even worked there a little bit before that, but that was the first time you worked in the coordinate plane with negative numbers. So let's jump right into it and kind of discuss what we're getting at here. Euclidean versus coordinate, right? The geometry that we've worked so far has been in a generic flat plane. So this flat plane that extends forever in all directions, right? This type of geometry is known as Euclidean geometry, and it was named after the mathematician Euclid, who lived about 2,300 years ago. But we're also going to be working with geometry in the coordinate plane, right? Where points are given specific locations using XY coordinates. Not surprisingly, this is called coordinate geometry. All right, so let's jump right into it in exercise number 1 and kind of get our feet wet with that. The 4 points A, B, C, and D are located at A, 3, 8, B, -7, -2, C, -9, 6, and D, 6, -4. Letter A, plot and label each of the 4 points. All right, well, this shouldn't take very much. I know that you've been doing this for years, and you did a ton of it in Algebra 1 when you had to plot points that lied on lines and parabolas and things like that. But let's kind of review it right now, right? If I'm looking to plot point A at 3, 8, right? Obviously, the 3 is the x coordinate, the left, right, and the 8 is the y coordinate, up, down. So I'm going to go 3 to the right, and I'm going to go 8 up, and I'm going to plot and label point A. Point B is at -7, right? So I'm going to go 7 to the left and 2 down, because that's at -2, and I'm going to label that point B. All right. What I'd like you to do now is pause the video and go ahead and plot points C and D. All right, well, point C is at -9, 6, so I'm going to go 9 to the left and 6 up and plot point C, and D is at 6, -4, so I'm going to go 6 to the right and 4 down, and that's going to be at point D. All right, so simple enough. One thing coordinate geometry allows us to do is specify the exact location of particular points relative to an origin, right? Relative to the point 0, 0. Let's take a look at letter B. Draw line AB and line CD. Label each. Okay, simple enough, right? We already talked about the fact that there's only one line that will go through any 2 given points. So as soon as we have points A and B, right, we can draw the one and only line that goes through them. So let's go ahead and do, oh my goodness, what happened? Point B, come on, is at -7, -2. This is going to be hard to get this thing exactly back to where I want it. Oh my goodness. All right, let me try to draw this line up here. Here we go, line AB. You'll probably have an easier time doing this for yourself than I will, but let's do this and let's label it line AB. More trouble than I thought it was going to be. Why don't you go ahead and pause the video now and draw line CD. I know you all love it when I have technical issues. So that's why I do them. That's why I have technical issues, just to entertain all of you. Okay, here we go. Line CD, simple enough. Hopefully simple enough. Move that out of the way. And we'll label that line CD. Okay, great. Let's take a look at letter C now. There is one point common to line AB and line CD. Label it point E and state its coordinates below. All right, well, hopefully, if you draw these 2 lines together with me, it will be obvious what point is common to both. Pause the video now, draw that point in with, a little filled in dot, and label it point E and state its coordinates right down here. All right, well, remember, we have a special name for what it's called when 2 lines share a point, or even 2 curves share a point in common, and that's an intersection point. The one and only intersection point of these two lines is right there, and it looks like it's 3 to the left of the origin and 2 up from the origin. So point E has coordinates -3, 2. All right, last little piece, letter D. Give an angle in this diagram that is congruent to angle AEC. Now remember, what it means for two angles to be congruent is for them to have the same angle measure. So the first thing I want you to do when you pause the video is locate angle AEC on the diagram and then come up with an angle that must be congruent to it. All right, well, let me change color really quick just to give us a nice contrast here. All right, here's angle AEC. All right, this angle must be congruent to it because it is a vertical angle. Right, and what angle is that? That is angle BED, angle BED. All right, easy enough. Now, this particular problem goes to show us something that is pretty important, which is that basically all the issues that we've been dealing with so far in Euclidean geometry, geometry that has no coordinates associated with it, we can also deal with in coordinate geometry, right? Points, lines, angles, vertical angles, congruent angles, etc. Okay, let's keep going and working more with coordinate geometry. It's a hard word to say. Most of the concepts we worked with in plane geometry, we will also work with in coordinate geometry. Let's take a look at exercise number 2. Given points E, F, G, and H located at E, -2, 6, F, 6, 2, G, 4, 8, and H, -1, -2, do the following. Letter A, plot and label all 4 points. All right, well, since we've reviewed that skill already, pause the video now and get those 4 points plotted and also labeled. All right, here we go. So E is at -2, 6. All right, F is at 6, 2. G is at 4, 8. And H is at -1, -2. Okay, simple enough. Letter B. Draw segment EH and line GH. Note the difference. Go ahead and do that. Draw segment EH and line GH. All right, let's do it. So in one case, I'm asking you to draw a segment. In the other case, I'm asking you to draw a line. And of course, they're related to each other, but they're not exactly the same thing. All right, so let's first draw that segment in. We just want the segment that begins at E and ends at F, or vice versa. Doesn't really matter. But then we want a line that passes through both H and G, all right, but doesn't end at them. Right, so I'm going to kind of extend this a little bit, hopefully, and get rid of my ruler. There we go. All right, now one of the other things, oh, actually this is part C, let's take a look at that. Label the intersection point of EF and GH, segment EF and line GH, as point I. State the coordinates of I below. All right, why don't you go ahead, right, put a dot where that intersection point is, label it as point I, and then state its coordinates. All right, here we go. Real easy to see intersection points, right? There it is, there's point I, and point I has coordinates of 2, 4. Excellent. Now, letter D. What special relationship do you think exists between this line and this segment? So what do you think? What do you think is true about this line and this segment? Well, one thing that you might note is it kind of looks like they're perpendicular to each other, right? Now, I can test that by bringing up a compass, right? rotating it like this, and seeing if in fact they're perpendicular. And they are perpendicular, all right? There's no question that, once we have our protractor up here, there's no question that this line and this segment are perpendicular to each other. The other thing that's true is that that line actually bisects that segment. And again, that one's a little bit harder to tell, but if you think about it, you go down 2 here, you go across 4 here, go down 2 here, go across 4 here. It's pretty obvious that this length and this length are the same, making I the midpoint of EF, right? So, in fact, the relationship that exists between these two is that GH is the perpendicular bisector of segment EF. All right. Now, if you just said it was perpendicular, or if you just said it bisected it, those are both great. Great observations, okay? And really, we're just kind of observing things right now in today's lesson, and we're getting this sense that all of these different things we've talked about, perpendicularity, right, vertical angles, lines, segments, points, all of them, we can also examine in the coordinate plane versus the Euclidean plane where there are no coordinates. Okay, let's keep going. Exercise number 3. Given the points M, N, P, Q located at M, -1, 4, N, 0, 4, P, -3, -3, and Q, 9, 6, do the following, right? Letter A, plot and label all the points. All right, why don't you go ahead and do that? All right, let's do it. M is at -4, 1. N is at 0, 4. P is at -3, -3. And Q is at 9, 6. Okay, easy enough. Letter B. Draw line MN and line PQ. All right, go ahead and do that. Oh man, where's my ruler? Did I give myself a ruler? I didn't give myself a ruler. All right, I'm gonna have to hand sketch these lines. That's okay. Well, maybe not okay, but it'll get the job done for right now. All right, there are our 2 lines. Again, it could be worse. All right, and letter C. What seems to be true about the 2 lines you drew in B? Go ahead and write something down. Well, if you said that they seem parallel, you're absolutely correct. These are 2 parallel lines, and eventually we'll have a way of telling that they're parallel lines. Nothing to worry about right now. All I want you to do is see that, all right, just like in the last exercise, we could have 2 lines that are perpendicular. Here, we have 2 lines that are parallel. All right. Man, I just needed a ruler. It's all I needed. Okay, exercise number 4. At what point or points would a circle with a radius of length 5 units and a center at 2, 4 intersect a line that contains the points -3, 8 and B, 4, 1? Use the grid below along with a ruler and protractor to help locate, let's see if I can get rid of this, to help locate the point or points. All right, great. So what I'd like you to do is go ahead and try to do all of exercise 4 on your own, all right? You're given a description of the circle, you're given a description of 2 points that lie on the line. See if you can figure out what point or points the line that passes through these 2 points will intersect the circle that's described here. Pause the video now and take a few minutes to do this. All right, well, we have to draw both the circle and the line. Okay, so I guess I'll start with the circle, which is a little bit more challenging. The first thing I'm going to do is locate its center, which is at 2, 4. All right, then the other thing I have to do is I have to draw it with a radius of 5 units. So what I'm going to do is I'm going to bring my compass over here, and I'm going to put the pointy point on 2, 4, and then I'm going to stretch the compass out 5 units. Maybe I'll mark a point that's 5 units away. 1, 2, 3, 4, 5. So I need to stretch my compass out to this point. All right, perfect. And then I need to draw a curve, circle, that has that radius. Okay, great. So there's my circle. Okay, I don't know that it quite got there, but I think it'll get the job done. Okay, so then I've got A at -3, 8, which is right here. I'll label that. And B at 4, 1, and I'll label that. Now I just need to bring my ruler over, try to do as accurate of a job as I can, getting it through those 2 points. Let's see. So close, come on. There we go. That's not bad. Okay, so I've got my line, I've got my circle, right? We can have both lines, circles, and all sorts of things in the coordinate plane. Looks like they intersect right here. That's at -7. Whoops, that's not at -7. That's at -2, 7. All right, and it intersects right here, which is at 5, 0. All right. Now, of course, you could have a line that intersects a circle twice, like it does here, or it could miss the circle entirely, right? It could be down here. Now, I really like exercise number 5. Let's take a look. Let's take a look at that one before we make our compass do the splits. Exercise number 5. Would the portion of line AB contained inside the circle be longer or shorter than the diameter of the circle? Explain. Awesome. So seems a little bit weird because I don't know the length of the portion inside of the circle, and how do I then compare it to the length of the diameter? Well, pause the video now and see if you can figure that out. All right, well, it's got to be shorter, okay? And it's got to be shorter because the diameter is the longest distance across a circle, and since the portion, of AB inside the circle, here we go, doesn't go through the center, hello, it is not a diameter. That took a little bit. In fact, let me just come up here real quick and let me get rid of that. Windows. Right? So the portion of this line that goes through the circle is here, outlined in red, right? So that portion doesn't go through the center of the circle, which is obviously located right there, okay? The segment that goes from one portion of a circle to another portion of a circle that is longest will always be the one that goes through the diameter. This one fails to go through the diameter and therefore must be shorter than it. Okay. One more problem. Let's take a look at quadrilaterals in the coordinate plane. Now we're going to work with many quadrilaterals, which are four-sided figures in the coordinate plane. I think it's Unit 6 that we devote to quadrilaterals, and we will do a lot of that work in the coordinate plane. So let's take a look at a little bit of that in exercise 6. Quadrilateral ABCD has vertices located at A, -4, 8, B, 8, 2, C, -4, -6, and D, -8, 0. Letter A, plot the points and draw quadrilateral ABCD. Awesome. So why don't you go ahead and do that, and then we'll get it up on the board. All right, well, I took the cheap way out on this one. I pre-plotted this one for you, okay? And there it is, simple enough. You can't see it all that well, but point A is up here, point B is there, point C is there, and point D is there. All right, so you can kind of see the points. Maybe I need to make the letters a little bit bigger, but there's our quadrilateral. Letter B, draw in segment AC and segment BD, the diagonals of the quadrilateral. All right, so for every quadrilateral and really every figure other than a triangle, okay, you have what are called diagonals. And diagonals are simply segments that connect one vertex to another vertex that's not adjacent to it. So the actual figure is there because we're connecting vertices with segments that are adjacent to them. But if I connect A to C, that's called a diagonal. And if I connect B to D, that's also called a diagonal. I'm going to just click and put them in right there. All right, why don't you go ahead and pause the video now and draw in those diagonals. All right, letter C. What type of special quadrilateral does ABCD appear to be? All right, now I don't want you to say an envelope, although it kind of looks like the back of an envelope here. That's not a special quadrilateral. Pause the video now and write down what you think ABCD is. All right, well, if you said a rectangle, you're completely right. If you said a parallelogram, yeah, you're also completely right. But the most special type of quadrilateral it is a rectangle. I kind of like the red, nice and bright. All right, so the point in this problem, again, is that we can put almost anything in the coordinate plane that we also can put in the Euclidean plane. Rectangles, triangles, angles, rays, lines, segments, circles, all of it. So let's summarize, right? We're going to do a lot of geometry both in the Euclidean plane, and that's where all we maybe have are lengths and angles and things like that. And we're also going to be doing a lot of geometry in the coordinate plane where we have like solid numbers about where points are, and that's going to allow us to calculate things like distances between points and midpoints and slopes, and we're going to be able to get into parallelism and perpendicularity. All right, and we're going to be doing a lot of that actually in Unit 2. This is the last lesson of Unit 1, and in Unit 2 we're going to start right away with what are called transformations, and much of that we're going to do in the coordinate plane because it's easy to give you a transformation rule in the coordinate plane. More on that though in the next lesson. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.